Hello, my name is Mertcan Inal. Today I will give a presentation about my topic, which is about the fault-tolerant controller design for multirotor systems. Before starting my presentation, I would like to thank to my university professor, Cosku Kasnakoglu. Then I would like to give some information about my academic career. I started my bachelor's degree in Top University of Economics and Technology in Ankara, Turkey, in electrical and electronics engineering. Then a few years later, I start my master thesis on fault-tolerant controller design for multirotor system, again in the same university program. In below, you can see my academic studies and publications. I have also few studies in the unmanned aerial vehicles, and I also some studies for the signal processing and design of the patch antennas. So I will begin with my purpose of this study. The use of area of the unmanned aerial vehicles is increasing day by day. However, engine failures, sensor failures, or communication failures may occur in quadcopters, and it causes both serious accidents in vehicles and damage the environment of surroundings. Especially quadcopters are applicable for a wide range of potential applications such as security, traffic surveillance, natural risk management, environmental exploration, agriculture, and military. The purpose of this study aims to develop a fault-tolerant controller design for a quadcopter to enhance its reliability and stability in presence of component failures or malfunctions. When we look at the historical development of the unmanned aerial vehicles, we can see the oldest use of these aerial vehicles in 1800s. In Austria, used 200 flammable balloons against Venice, and those balloons used as the unmanned vehicles, and they are carrying flammable equipments. Then they used such balloons to conquer the city, and in 1930s, you can see that America made the Bosat helicopter. The Bosat helicopter, also known as a Jerome de Bosat flying octopus. This one was an experimental quadcopter helicopter. It was built for the United States Army Air Service, and it was said at the time to be the first successful helicopter. And as you can see nowadays, and we have modern quadcopters, and they can be equipped with the different devices such as cameras or sensors, or they are useful for different purposes. So in this study, I designed a quadcopter in MATLAB Simulink program. So there are few steps of the controller design in such programs. So in the quadcopter system design, I used mathematical position of equations of the quadcopter, and I used Euler formulas for the description of the movement diagrams and movement of the quadcopter dynamics. And model design is done in the MATLAB Simulink by determining the dynamic equations. The design model also includes the effects of the external disturbances and possible failures. I will show you how I determine such disturbances in the system. So, as you can see, the movement axis of the unmanned aerial vehicle. On the left side, you can see the aircrafts, and on the right side, you can see the basic quadcopter. And there are three basic movements, and we call them as pitch, yaw, and roll. And there are three different axes, and the terms are used to describe an airplane's movements through the air. There are in fact 6 degrees of freedom of a rigid body moving in the three-dimensional space, as the movement along each of the three axes is independent of each other and independent of the rotation about any of these axes. The rotation has 6 degrees of freedom. So on the left side you can see the pitch movement, also you can see over there. So when we turn the aircraft on this axis, you can see that the aircraft's nose up and the tail will be down, and on the other opposite side you can see the tail up and nose down. And when we check the yaw axis over there, which is right over here, and when the aircraft turn over this axis, you can see that the nose movement from side to side over here, and the tail side is over like a clockwise. And also for the roll axis, you can see it's when we turn this axis, you can see that the aircraft's wings are making movements along over here. So it is like a clockwise movement again, and all of the body of the aircraft making movement over here. So you can see the same movements for the quadcopters. So for the other step is the fault detection. So we should define the fault in the system. So proposed system has a closed loop control system in order to detect the anomalies and the sensors, motors and critical communication modules. After realizing the abnormalities, a fault identification algorithm determines the specific components responsible for the observed abnormal behavior. So in this study, motor failures and abnormalities are examined. As you can see that this is the simple methodology of the feedback control system. You can think that our plant is the aircraft, and we have sensors in the aircraft, and here is the controllers. So when we give this signal over here, you can see that there's an error signal because of the disturbances over coming through the plant. Then the signal goes to controller, and then it goes to plant. But you can see the feedback signal is coming from plant to sensors. So the sensors identifies the abnormalities over here. So this is our disturbances, such as wind, such as abnormalities of the aircraft. So then the signal returns back to the controller. Then there's a sum of the incoming signal and the feedback signal. So the fault is getting low. So at the end, we should see our desired signal. So I can show the graph of this. So the other step of my study is fault isolation. In order to prevent motors having faulty behaviors from the distorted signal, PID feedback control system is proposed. Quadcopter roll pitch yaw movements are tested by reference signal. As you can see on the left side, yellow is our random P reference signal, and the blue one is the output of the signal. So the blue signal actually track the yellow signal. So you can see the amplitude is changing through the signal's amplitude, the yellow signal's amplitude. Also on the right side you can see the step response of the system. So in the response to different signal inputs, the outputs of the system are examined under the white Gaussian noise. The proportional controller is dependent on the current error. The integral controller is the sum of the past errors, and the derivative controller is an estimation of the future errors. So you can see that after few time after, you can see that the error is fixed by the controller. When we tune the PID controller values, we can achieve the better state responses, but the curve settlement time increases. So you can see that the settlement time is increasing, but when we tune for the better curve settlements, we will have the more aggressive output signal. So as a conclusion, I can say that our proposed PID controller has ability to fix the errors under disturbances. However, nonlinear controller methods have better ability to control the system. And on the other hand, when we decrease the curve settlement time, we observe more aggressive system behavior. For more robust system error isolation, nonlinear quadcopter system will be tested with the nonlinear controllers, such as sliding mode control. There are few methods of the nonlinear systems, so I will also create different simulations to test the nonlinear system. And lastly, you can see my references over here. I used different sources to combine different informations. Then thank you for your time. I hope this short presentation has given you information about the working principles of the unmanned aerial vehicles and the quadcopters. If you would like to ask few questions to me whenever you want, you can reach me out with my email address. Again, thank you for this organization. I hope you have a good day. Bye.